Okay, the section that we focus on in this video is the elementary row operations and what they are used for in matrix algebra. We will learn about the following important ideas: Gaussian reduction, Gauss-Jordan reduction, as well as Cramer's rule for solving systems of equations. Let's see how this works. Okay, let's introduce Cramer's rule, the last focus for this video. Now, what Cramer's rule allows you to do is it allows you to solve x or y or z without having solved all the others. That is the purpose of Cramer's rule. But of course you can use Cramer's rule to solve all three variables as well. Let's see how it works. It's an explicit formula for the solution of a linear system of equation with as many equations as unknowns. Remember, that makes it square. Not square, it makes a coefficient matrix square. Valid whenever the system has a unique solution. And we've seen when there's no solutions, where there's many solutions, and when there's one and only one solution. Okay, so Cramer's rule is a handy way to solve for just one of the variables without having solved the whole system. That's the point of this rule. Instead of solving the entire system, you use Cramer's rule to solve just one single variable. Now that should get you excited. Let's see how it works. Cramer's rule works on determinants to solve systems of linear equations. Let's see how it uses the determinant. Well, first of all, we need the coefficient matrix, A, and then we need the column matrix, 7/2. Notice that we are not augmenting them. We keep them separate. The very third thing we want is the determinant of the matrix A. Now that determinant, you know by now, is the product of that minus the product of that, gives you a determinant of 7. Okay, now the process starts. We've got all the information that we need. Now, if you want to solve for x, folks, if you want to solve for x, you are going to replace the columns with the x's in it with this column matrix B and find the determinant. Okay, so you do what? You will now find the determinant AX. We're going to call that determinant AX. What do? We take A and we delete the column for the X entries. That's the first column. We replace it with this matrix 7/2. There we go. And for that we find the determinant. 28 plus minus 2 rather is 26. And there we have AX, very important, is 26. Now we do the same for the Y column. We take the Y column here, minus 1, 4. We replace it with the column matrix. We find the determinant AY. That is 29. Okay, so we've done what we are supposed to do. There's two variables. We need two determinants. And now for the solutions. Now look at how lovely this is. The solution for X, you take the determinant X divided by the determinant of the matrix, and there's your solution. You do the same for Y. The determinant for Y divided by the determinant of the initial coefficient matrix gives you the solution for Y. Wow, that is fabulous. That helps you to find a particular point without having solved, or particular solution for one of the two variables without having solved both of them. Okay, so if the determinant of the coefficient matrix, obviously here, was 0, we were in a trouble spot because we will have zeros there. Now that will lead to no solution. There will not be a solution, but we won't know why there won't be a solution. Okay, so let's see. We'll talk about that in a minute. Let's consider this system over here. The coefficient matrix is formed, but now we have the determinant of 0. Now that's a problem. What does this mean to us? We aren't going to get a very nice answer. In fact, we aren't going to get any answer possibly. Okay, why? Either the lines are parallel or they are the same line. If they're the same line, there's an untold number of solutions. If they're parallel, there's no solution. They will never intersect. Now, the question is, the only problem is how we can find out which is which. And the way to go about it is to go back to elimination. Now, let's just have a look. If I divide this by -3, folks, then I get x minus y is minus 2/3. If I divide this by 7, I get x minus y is 8/7. Because these two y values are different, it means that we are working with parallel lines. There's no solution. Remember, if we divided by -3, we formed x minus y. Dividing by -7 also forms x minus y. So we will have this side equal. The only thing is to compare those two. If those two entries were also equal, we had the same line. So there's an enormous amount of answers that you can find for this system, if that was the case. Okay, there's a third system for you. I want you to solve the system using Cramer's law. Pause the video and then come back and see what you did. Okay, let's have a look. We have our coefficient matrix. We also have our column matrix B, and now we need our determinant. So I'm going to work with the determinant by augmenting the coefficient matrix with the first two columns and then following the product that we learned in previous videos. Okay, now remember, there's a big bracket around this section over there because you're taking the entries you found by this way, multiplying, you're subtracting it from those entries. So this whole thing must be in a bracket. Once it's in a bracket, you'll see it changes all the plus signs to minuses. Okay, so don't forget to use your brackets. I've already included the change of sign over there. Okay, so if we calculate that, we get a determinant of minus 141. Okay, so let's see. What do we know? We have the determinant, we have the column matrix, and we have the initial matrix. So now we want to find AX. So we go to the X entries and we replace them with the column matrix. Okay, and I need the determinant. So again, I augment this new matrix with the first two columns and I find my determinant over there. Once I've calculated my determinant, I see it's minus 1,499. Quite happy with that. Okay, so to find the X value, I divide this determinant by that determinant and I get my result over there. Okay, now the same for Y. I will go back to this initial coefficient matrix and I will replace the Y column with the column matrix 10, 11, 12. From that matrix I augment it to find my determinant. My determinant is minus 1492. I divide it by the determinant of the initial matrix and that's my result for Y. Okay, there's one left. For Z, we replace the third column, we augment, we find our determinant for a Z, we divide it by the determinant of the initial matrix, and there we have it. We've got minus 16/41. So the solution for this system is indeed those three numbers. If you got that, pat yourself on the back. Brilliant. It's not that difficult. Just remember, work slowly. Okay, there's a few exercises for you to do if you want to practice what we've done for today. My face is in the way there, so I'm going to try and remove myself there. But yeah, it seems like I am not going to be able to remove myself. So the first one, now there we go. That's it. So take a shot of that screen. There's 1, 2, 3, 4, 5, 6, 7, 8 problems for you to work on. Work with Cramer's rule for each one of those, and also then work with Gaussian Jordan reduction. Compare your two results at the end of the day. Okay, so for Cramer rule, it's possible to determine whether the system has a solution, one solution, or infinitely many solutions. Remember what we looked at in the last slide. So if the determinant of the coefficient matrix is naught, then you're done, folks. You don't have to do any more work, because the coefficient matrix had a determinant of naught. There is no possible solution. So you check, does it have infinitely many solutions, by looking at coefficients in your matrix. Now here already I can see 2x, 3y, but there's no y over here. So if there's things that you can do, and when you consider many reductions or many solutions or absolutely no solutions, look at the coefficients of x, y, and z and see what they give you. Okay, so here the system may be inconsistent, meaning it has no solutions, or dependent, which means it has an infinite number of solutions, which we may express in parametric solutions as a plus 3, and a minus 4. You'll have to use some other method, such as matrix row operations then, to solve the system. The moment you get a determinant that's naught, you use alternative methods to solve it. Okay, so basically we're saying if the determinant is naught of the initial coefficient matrix, you cannot solve the system. Okay, folks, that takes care of our focus for this video. Please, if you learned something, like the video, share the video, and comment on the video below, and also subscribe to my channel so that you can get updates on videos that I post.